Alright, so hello and welcome everyone to week 12 of interactive live sessions for the course on computational fluid dynamics for incompressible flows. As we all know, this course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. And one quick note, so tomorrow from the same time, 6 to 8 p.m., we will have a revision class as well. That will be our last session together. Alright, so without any further ado, let's move on to the first question of today's session, which is asking us that for solving the Navier-Stokes equations using finite volume method, what are the disadvantages of using a co-located grid? The options being option A, that the pressure difference between alternate grid points are taken. Option B, the velocity of the cell center does not appear in the continuity equation. Option C, that wavy velocity or pressure fields are treated as constant fields. Or is it option D, all of the above? That is, all of options A, B, and C are correct. So for solving Navier-Stokes equations using finite volume method, FVM here stands for finite volume method. What are the disadvantages of using a co-located grid? And co-located grid meaning that you know the all the quantities, be it pressure, be it velocities, be it you know some other scalars like temperature or any scalar for that matter, they are all stored in the cell center of each cell. That's what a co-located grid means. So here are the four options for the question. Option A being that pressure difference between alternate grid points are taken. Option B being velocity of the cell center does not appear in the continuity equation. Option C being that wavy velocity or pressure fields are treated as constant fields. And option D being all of the above. Let's take a look at the solution. It's actually option D, all of the above, because see, we have seen this. So for a co-located grid, let's say like this, Now, the first point, pressure difference. So, if we want to find out dpdx over here at say P, this is P, point P, not pressure P, and we have one east cell and one west cell. So this will ultimately boil down to PE minus PW divided by 2 delta x. Delta x being the constant difference between these two. So you end up taking uh, pressure differences between alternate grid points. You miss out P. You take W then E. So your effective mesh size is double that whatever you have considered. So this is a loss in accuracy which we do not really desire. Then another disadvantage being option B, saying that velocity of the cell center does not appear in the continuity equation. So for this same template, we are considering a 1D case. So here, if we are trying to solve the continuity equation, it should have been just du to x equal to 0. So here also we will get uw minus ue being equal to 0, right? And this will be of course multiplied by something, but anyway, so this is what we end up getting. So here also the velocity up does not really appear in the equation. So this that is statement B, both of which are correct, by the way. And then the last one, wavy velocity or pressure fields. This we have seen earlier. So if we have something called checkerboard velocity field or checkerboard pressure field, that is treated as a constant field. So we saw this in the finite difference method. It's no different here. So let's say if we have a pressure field like this, 200, 100, then 200, then according to the equation above, the dp dx at this point will be equal to 0 because it takes a difference between this point and this point, which is 0. So that also introduces an error in the equation, in the whole solution. So since all of these are true, you should have picked option D, all of the above being the correct answer. Alright, so moving on, we are on to question number 2, which is asking us a different thing, which is asking us for solving again Navier-Stokes equations using finite volume method. Now, what are the advantages of using a staggered grid instead of a collocated grid? We saw the disadvantages of a collocated grid. Now we are looking at advantages of a staggered grid. The options being option A, pressure differences between adjacent grid points become natural driving force for velocity components. Then statement B says that difference of adjacent velocity components appear in the continuity equation. Option C being all of the above, so above meaning both A and B. and option D being none of the above. That these are not the advantages of using a staggered grid. Let's take a look at the solution. It's actually option C, all of the above, meaning that both A and B are true, and they are. We will look at them. So, the first one, pressure differences between adjacent grid points become natural driving force for velocity components. So, here again we will take a 1D example. So, we have a pressure cell like this, and then for velocity, let's say we have a cell like this and another pressure cell over here. You get the point, right? So these are the velocity cells are staggered in this manner. So U is stored over here, and we have P over here, and we have PE over here. So for U, this pressure difference PP minus PE, this becomes a natural driving force for you, right? So similar thing for V velocity also. If we have staggered grids in the Y direction, the pressure differences across that U cell becomes a natural sort of driving force. So since there is a pressure difference, there will be a flow. There will be an increase in the momentum in that direction. Now, the second one, that differences of adjacent velocity components appear in the continuity equation. Once again, so if we just uh, consider something like this. Uh, so let's say we have two different U cells like this, and we have a P cell in between. So we are trying to find out the continuity of this cell over here. So there is a UP over here, and there is a UE going out through that side. So in this case, the continuity equation will have UP minus UE. So sorry, this will be small letters. So, U of that cell and U small e going outside. So not P, this will be small w being equal to 0. And if you have V in the y direction, that will also come up. So basically, you are taking one cell and only considering things that are, you know, coming in and going out of that cell. So it makes much more physical sense that, the continuity equation being the divergence of uh, flow in that region really makes sense over here, since you're uh, integrating the flows coming in and going out within one control volume, being the cell that you are focused on. So both statements A and B are correct, and that's why option C, being all of the above, meaning A and B, are correct. And option D is false. Right. So moving on, we'll move on to question number 3, asking us what is simple in CFD? Simple method in CFD. Is it option A, semi-implicit method for pressure-linked equations? Is it B, spectral implicit method for pressure-linked equations? Option C, simplex method for pressure-linked equations? Or is it option D, spectral implicit method for partial differential equations? Let's take a look at the solution. It's actually option A, the first one, semi-implicit method for pressure-linked equations. So this was a method invented by Dr. S.V. Patankar, and it's called, so let's break the name down, pressure linked equation, because this really links the velocity with pressure, which is one of the challenges uh, when you're trying to solve the Navier-Stokes equations, because the, these sort of things doesn't really appear in uh, these standard convection diffusion equation. There's a source term, of course, but that source term is rarely linked with the uh, actual physical quantity so much. But pressure and velocity, as we know, are quite intercoupled with each other. So linking that is one challenge which is solved by this method. And the second is the nature of the method being semi-implicit. So if, you'll see in the actual method, the velocity equation is implicit. So there we have something like APUP equal to ANB UNB plus, some pressure correction term and some source term, which I'm sort of taking into account within this B. So this equation is implicit, but later on we also solve for a pressure correction equation in which we drop this term, the PP and B prime. So this term is dropped. As a result, this method we can't call fully implicit. It has to be called semi-implicit. Right? Okay, so moving on, we move on to question number 4, which is asking us what is the difference between the simple method and the simple R method. Simple R being simple revised. Is it option A, that simple R or simpler uses an additional velocity correction equation? Option B, being simple, uses an additional velocity correction equation. Option C, simpler is a fully explicit method. Option D, simple is a fully, sorry, implicit method. Let's take a look at the solution. It's actually option A, that simpler uses an additional velocity correction equation. So uh, this method is faster than the simple method. It takes fewer steps, but each step or each iteration has a additional equation to be solved, which is the other velocity correction equation. But overall, the simpler method is uh, better and quicker than the simple method. Okay, so moving on, we'll move on to question number 5, which is asking us what is the main advantage of using the simplex algorithm or simple C algorithm, being simple corrected over the simple algorithm. Is it option A, that it can handle compressible flows? Is it option B, that it does not require under relaxation? Option C, that it is more computationally efficient? Is it option D, that it is better suited for unstructured grids? So simple C meaning simple corrected. Let's take a look at the solution. It's actually option B, that it does not require under relaxation. So the thing is, in simple method, we add the pressure correction terms to the previous provisional pressure terms, right? So what happens is that since this pressure correction term is calculated after a lot of assumptions, there might be some mistakes which have creeped into that, and so it might overshoot the actual uh, you know result. So let's say if this is your correct P that you're trying to get, and this is your P star, and you start off someplace over here, and after each step you add some delta P prime correction to it. So let's say you're going this way step by step, and it may so happen that you may overshoot the actual correct solution. So what is done to remedy this, that there is a under relaxation factor which is multiplied to this correction term, usually between zero point 0.6 to zero point 0.8, but then again you have to play around with this number and find out what's optimal. So that sort of slows down the convergence but makes sure that it does not diverge away. So we sort of slowly approach the solution. In it may take more steps, but we do not overshoot the correct solution. Now, what the simplex algorithm does is that it improves the pressure correction term. So, the pressure correction term in simplex is actually better. It has less assumptions going into it, and so therefore it reduces the chances of overshooting the correct solution as well. So that's why it does not require under relaxation. That's one of the main advantages of the simplex algorithm. And since we do not need under relaxation, we can, achieve the correct solution maybe in fewer steps. Who knows? Because under relaxation definitely slows the convergence down. Alright, so moving on, we'll move on to question number 6 of today's session, which is asking us what is the purpose of the pressure correction equation in the simple algorithm? Is it option A to correct the velocity field for the pressure gradient? Is it option B to correct the pressure field for the velocity divergence? Is it option C, that is to correct the turbulence model for the pressure gradient? Or is it option D, to correct the mesh for the pressure gradient? Okay, let's take a look at the solution. It's actually option B, that is to correct the pressure field for the velocity divergence. So it's the velocity divergence which sort of gives us the convergence criteria, right? The summation of FF being equal to 0. So it originally is not equal to 0, but as we go through more steps and as we approach the solution, it should tend towards 0. So getting the pressure correction gives us uh, the velocities, velocity corrections which are linked to it, and these velocity corrections go into the velocity divergence equation, which uh, goes on to check for convergence and tell us whether to run for another step or whether we have reached the correct solution or not. All right. So moving on, we'll move on to question number 7, which is asking us that in the simple R algorithm, the pressure correction is performed after solving the pressure correction equation. Is it true or is it false? Simple R being, so I missed this earlier, so this being simple revised. So it's a simple true or false type of question. The statement is given, the statement being that, sorry, that in the simple R algorithm, pressure correction is performed after solving the pressure correction equation. Is this statement true or is it false? Let's quickly take a look at the solution. It's obviously false. So the pressure correction has to be performed after solving the pressure correction equation, which gives us the correction P dash. We add that onto the uh, provisional value of pressure and get the newer value of pressure which we use for the further iterations. Okay, so moving on, we'll move on to question number 8, which is asking us that in finite volume method, if velocity at the boundary is known, that is, if it's a Dirichlet boundary condition for velocity, how is the boundary condition handled? Is it by option A, by taking the pressure gradient to be zero, or is it by option B, by taking the pressure correction gradient being set to zero? Okay, so let's take a look at the solution. It's actually option B, that the pressure correction gradient is set to zero. So basically, our velocity correction is linked to the pressure correction, right? So since we know the velocity, we know that this. Okay, this is a function of the. With some constant being multiplied. So basically, the pressure gradient is not really like this. So it is some constant multiplied by the, so let's say at the boundary, if this is our boundary, let's say, and this point we call as B, and we will have, let's say, another face E over here, and there might be some N and S as well, but we don't care about them for now. So U being this way, so U prime B at the boundary, that is some constant into, the pressure at some fictitious point here, being, let's call it PW, and some PP here, something like this, right? So this difference is similar to the uh, the pressure gradient. So some C prime, or let's drop the prime because prime means correction here. Let's call it C1, some other constant into dp prime dx. And since we know the velocity, the correction is not required, right? So correction is zero always. Since we know the exact value of ub. So since this is zero, the gradient of pressure correction also has to be zero. So that's why if we know the velocity, then the pressure correction gradient is set to zero. On the other hand, if the pressure is known at the boundary, then the pressure correction itself is set to zero at the boundary instead of the gradient. Because then again we know the pressure, so we do not really need correction terms to improve over it. We already have the solution at that. Got it? Okay. So moving on, we'll move on to question number 9, which is asking us what is the correct step of sequence. So the correct sequence of steps in the simple algorithm. So 4 steps are given here. You have to arrange them in the correct order. So the steps are: step A, check for convergence; step B, solve the pressure correction equation; step C, solve for the velocity field using the guessed pressure field; option D, update the velocity and pressure fields using the corrections. So there are 4 options given below. Option A being BCDA being the correct sequence of steps. Option B being CBAD. Option C being CBDA. Or is it option D ADCB? So let's take a look at the solution. It's actually option C, CBDA. So let's go through this. So option A being check for convergence, this always has to be the last step, right? So then the first step has to be to solve for the velocity field using the guessed pressure field. So first step would be to guess the pressure field, and the next step would be to solve for the velocity field using the guessed pressure field. So C being the first step. Then once you have the velocity field, you have to use it to solve the pressure correction equation, being step B. Then once you have the pressure correction equation, you have to update the pressure field as well as the velocity field using those corrections. So that being step D. So see, and then you have to check for convergence and run the whole sequence of steps once again if needed. So that gives you the correct sequence of steps being CBDA. Hope that's clear. We will move along to the next question, which is question number 10, which is asking us what is the correct sequence of steps. So, same question about the simple R algorithm. Once again, the steps are step A, solve the pressure correction equation. Step B, calculate FF hat and solve the pressure equation. Option C, solve for U star, V star and calculate FF star. And then option D, update the velocity field using the velocity corrections but not pressure. So the sequence of, we have a few options having different sequences, them being option A, BCAD, option B, CBAD, option C, CBDA, and then option D, ADCB. Okay, so let's take a look at the solution. It's actually BCAD. So first of all, uh, using the FF prime, FF hat, sorry. So we first of all find the U hats, the U hat, V hat and all that. Then we find the FF hat and we use it to solve the pressure equation. We have a pressure equation which gives us directly the pressure, and we uh, do not and we also have a pressure correction equation which is solved later. We do not use it first step. So the first step would be option B, to solve the pressure equation and whatever we need to solve the pressure equation being U hat, V hat and FF hat. Then after that we we get the pressure equation which we did not guess. We got a pressure equation, and using that pressure equation we find out what U star V star is, and we also use it to calculate FF star, which we use to check for convergence. So that's the next step, C. Then once we have done that, then we can solve the pressure correction equation, which we do now, and then using that we correct the velocities only. So we only correct, so only find the U prime and V prime and not P prime. because velocity, once again, we will solve in the uh, uh, pressure equation in the next step using the updated velocities. So then last step would be to update the velocity fields using these corrections that we found, but not pressure, because it will be solved using the pressure equation. So the correct steps, sequence of steps would be BCAD. Alright, so that was the last question of today's session. Thank you all for being here. We will meet again tomorrow, that is 16th of April from 6 to 8 p.m. That will be a revision session and the last one for this course. Alright, thank you.